Welcome back as we continue that journey through the use of exact values trick. Obviously, when we get challenged with things in mathematics, we don't always jump to the initial conclusion that we need to, and sometimes that can be a bit distressing, not knowing quite what to do. But if we think about the form of this particular example, this has a set form, and this is often a regular thing with these particular problems. So cos, sin, with a minus in the middle, is in fact cos alpha plus beta. So in actual fact, this question is trivial in that it is asking cos 45. And as we know, cos 45 is the x of the 45-degree triangle. We're both the same size, and that is 1 over root 2. 1 over root 2. Now often, not always, but often 1 over root 2 has been realised. So that means multiplying by 1. And the form of 1 is to take the rationalised, I said realised, but rationalised. So the squaring of the 2 leaves 2 on the bottom and simply root 2 on top. So that's the same form as this one, just looks different. Often, if you're given a question and it has this in it, you have to cognate that it's a 45-degree triangle. Alright, so for part B, it's a similar thing. Sin cos plus cos sin. Well, sin cos is written around the wrong way, isn't it? But this is, again, a sin alpha plus beta. Now in this case, alpha can be x and beta can be 2y. So alpha 2y. Alright, it's algebraic, and so that's where it ends. Okay. Alright, so very interesting the way these unfold. Very interesting the way they are hidden and need to be interpreted. But nevertheless, that's how we go. Alright. So the next one is of a similar ilk. It's a result. It's a result. So it wants us to show that cos alpha minus beta is 1 tan alpha. So this is a very straightforward one. So if we take the left-hand side, we've got cos. This will be reduced into, this is an algebraic form, a bit more like what happens in extension 1. So cos beta. So this gives us on expansion cos alpha cos beta plus sin alpha. So I wouldn't be expecting students to remember these. Just use your sheet. Sin beta over cos alpha. Now, what does that look like? Well, it's always the not so obvious things that make a difference. And the not so obvious things are that we've got to split fractions. So if we split the fraction, we get cos alpha cos beta over itself plus sin alpha over sin beta. What can you see there? So we've got to split the fractions so they're both the same family, but we've gone back. What do you see? And what about this one? So this one's one in disguise, isn't it? However you interpret that, to 1 sine over cos times sine over cos. That's right, tan. Tan alpha, tan beta. Which equals the right hand side as so very straightforward. Alright, so after this we look at our examples and essentially it's a similar thing. So what do we end up with? Sine cos, because it's a minus. So I'm not going to do the whole rewrite of alpha and beta. Sine 90 cos theta. Now it doesn't mean that simply because it's algebraic things aren't going to cancel. Cos 90 and sine theta. So if we go through and think about our exact values trig, sine 90 is here. So this is worth 1. Cos 90 is here. What's cos? X. This one's 0. The diminishing triangle is going to 0. So this whole term, this whole expression is 0. It's gone. So all we're left with is 1 times cos theta minus 0, so we don't have to bother with that. So we get cos theta. And that's your final answer. Okay, so they're very interesting, aren't they? No problem though. So cos 90 minus will be cos 90 cos theta plus sine 90. Seems ridiculous, doesn't it? Cos 90 we worked is 0. 0 times this term is gone. So sine 90 again is 1. So we'll miss those couple of steps. And all we're left with is sine theta. Very straightforward. The equivalent for this is tan 90 minus tan theta divided by 1 plus tan 90 times tan theta. So tan 90 is not defined, is it? Not defined. Tan 90 because it's asymptotic to pi on 2, plus or minus pi on 2, which is what that is. So another way to do this is to think about it as, let's start again, tan 90 minus theta is equal to sine 90 minus theta over cos 90 minus theta. And what do we have for that? We worked out that sine 90 minus theta up here is cos, and 90 minus theta up here is sine. So it's cot. to cot. Cot theta. Very interesting. Alright, so we can go on and continually do a similar thing. So we'll have sine 180, sine pi, cos pi. So we're going to get sine 180 is here, 180 degrees is here, pi. So the sine of that is 0. Cos of 180 is minus 1. So we're going to end up with minus sine theta. Now, I've got to tell you, you can check these with our technology as well. So I'm just going to put that in. And just to show you that one, use your brackets, 180 minus theta. Going to be algebraic sine 180 minus theta. And what can we ask it to do with that? Simplify it. In any case, while that's chugging away, could be very busy on the internet here. So we've got cos 180, cos theta, plus sine 180, sine theta. So this again is 0, so that term's gone. This is minus 1, so we get minus cos theta. And again for tan 180 is a multiple of 90, or pi on 2. Okay, so I'm not even going to finish it because it's not defined. So we can just put tan of 180 is equal to the sine. And we just did those, so we get minus sine over minus cos, which is sine over cos, just rise over run, which is tan. So from these you can develop all of your parts. So how do we go there? Oh, we didn't like it. Okay, simplify sine 180 degrees. No, I'm going to put degrees. or I can make it pi. Alright, I'll leave that with me and I'll work on that to get that back to you. Alright, so actually it didn't use some alternatives before, did it? Equals. Just do one more thing. No, it doesn't like it. Very interesting. So it's managed to pick that out okay. But it hasn't done anything else. That's fine. Okay, so we'll keep going. Show that if two lines are perpendicular, then their product is -1. So I'll fit this in now, I think. So essentially what we've got are two lines, and they can be arbitrary in their nature. And we'll assume that they're everywhere right angles. And then if we look at some angles here, we can see this would be alpha. This one over here would be gamma. And the whole angle beta. This one here we'll call beta. So these have got their general forms. So we'll call this one yt equals mt x plus b. This one here we'll call yn, which equals m x plus b. Now looking at these angles here, we've got 180 there, so the tan of alpha using the equivalence so lambda will be equal to 90 minus alpha. That's from inside the triangle. The internal angle is 180. So by the time we take out that, okay, equivalently we have in terms of beta. I'll let you experiment in how they were developed. So they end up with tan using one form, we've already seen that that's undefined, so that's cot. So we did it the other way. The other tan is tan 180. Minus beta, which we've worked out is minus tan beta. And so what we've got here is cot is minus tan beta (1 over tan alpha) is minus tan. And in solving this, we can call these guys the rise over the run. So we get 1 over mt is equal to minus m normal. If we solve that, or at least rearrange, we will get mt times mn is equal to minus 1, which is our very much used equation for gradients. Alright, that's just about 20 minutes, so we'll come back to the next one after this. Back soon.